we left off discussing this example. This is an example of a very simple model with two equations and two unknowns. And what we're going to do is write this equation system in matrix algebra form. Then we're going to solve it by using the inverse of the coefficient matrix. And what's nice about this process, solving an equation system by using the inverse, is it's exactly the same method whether you have two equations and two unknowns or whether you have 100 equations and 100 unknowns. It's the same exact process. The only difference is finding the inverse of a matrix that's 100 by 100 is a lot more difficult than finding the inverse of a matrix that's 2 by 2. But you could always use the computer to find the inverse for you. And that's obviously what you'd do if you had an equation system with a coefficient matrix that was 100 by 100. You wouldn't try to do it by hand. You would use the computer to find the inverse for you. But it's the same exact methodology. Okay. Here was the problem we were discussing. x1 plus x2 equals 2. And 2x1 minus x2 equals 1. Okay. In this case, our coefficient matrix is just this 2 by 2. 1, 1, 2, minus 1. Okay. And what's the first step? And now what we want to do, notice this equation system can be written as ax equals d, where this is the coefficient matrix. X is the vector of variables. And d is the right-hand side vector of constants. Our goal is to find A inverse, the inverse of this coefficient matrix right here. Once we have A inverse, then we could just pre-multiply both sides of this equation system by A inverse, and we would get A inverse A x equals A inverse d. And A inverse times A is just the identity, so it's Ix equals A inverse d. Then we can delete the identity, and then we just have our solution vector then. X star equals A inverse d. So that's the method we're going to use to solve this equation system. We know what A is. We have to find A inverse. Now, the formula for A inverse is simply this. A inverse equals 1 over the determinant of A times the transpose of the cofactor matrix. So the first step in finding the inverse is to do what? What's the first step in finding the inverse? Lucy? Find the determinant. And in this case, Lucy, what is the determinant of A? All right, to get the determinant of this, we multiply this times this. Minus this term times that term. So do you want to revise your answer, Lucy? So when you multiply this times this, you get minus 1. Yeah, minus this times this, so it's minus 1 minus 2 is minus 3. Okay. So the determinant of A is minus 3. Do you all see that? Okay. All right. The next step is to get the cofactor matrix. Now, this cofactor matrix, matrix C, is just this. C11, C12, C21, C22. That's the cofactor matrix. If we transpose that, then we get what we want. But let's first find the cofactor matrix. What is C11 going to be? What is the cofactor of this element? Right there, that'll be C11. So what is the cofactor of that element? Yeah. You just take the minor, which is found by deleting the row and the column, and that just leaves you with a -1. And since 1 plus 1 is 2, even number, you don't change the sign of the minor. So it is just -1. That's what you said, wasn't it, Ben? Was it Ben? You didn't answer? Who answered? 1. Oh, it's not 1. It's actually -1. Okay. Now, do you all see that? C11 is just -1. Okay. I'll let you answer this one, Ben. What is the cofactor of this element? You shouldn't have to use your calculator to do this. Anybody? Did you want to answer, Ben? No? Okay. Yes, it's going to be -2. Because, Lucy, you take the minor's 2, but now the subscripts on this element are 1, 2. Odd number, so that means you multiply the minor by -1. So it's a -2. Okay. What's the minor of this element? Right here. Yes, a -1. Again, the subscripts on this are 2, 1. Odd number. The minor, when you delete this column, this row is 1. You change it to a -1. Okay. And finally, what is the cofactor of this element right here? Is it a -1? Brittany, that's all right. Okay. What is it, Jonathan? Yeah, it's just 1 because the subscripts on this are 2, 2. That's an even number, so then you just take the minor, and you don't change the sign, so it's just a 1. Okay. So that's the cofactor. It's easy to get C transpose now. C transpose is just this. We just transpose this. So we take this row right here, make it into a column. Take this row, and in C transpose, it becomes the column, the second column. Okay. So next is easy. Once we have C transpose, then you just calculate A inverse. And it's just 1 over the determinant of A multiplied times C transpose. So it's 1 over -3 times C transpose. So A inverse is just this. One over a -3, I'll just put that in parentheses, times this C transpose, which we found. If I multiply, this is scalar multiplication. So if I multiply each of these elements by -1/3, I could just write A inverse this way. It's a 1/3, 1/3, 2/3, and a -1/3. Okay. Now, we've gone through quite a few calculations to get this. How could we be confident we haven't made a mistake? How could we be confident that this matrix right here is indeed A inverse? Exactly. Multiply it by A, Johnny. And if we get A times A inverse is equal to I, then we know we have the inverse. Because the inverse is unique. So if you check that, we should get the identity. Let's just make sure that works. Who knows? Maybe I made a mistake. So let's just check. Let's multiply. You could do it either way. A inverse times A. Let's do it that way. So it's 1/3, 1/3, 2/3, minus 1/3 times A. I haven't erased our A matrix yet, have I? No. It's 1, 1, 2 minus 1. If we do this multiplication, we should get the identity. First row times first column gives us 1/3 plus 2/3, 3/3, or 1. So far, so good. First row times second column gives us 1/3 minus a 1/3. Oh, good. There's our 0. The first row looks good. Now we take the second row. Second row times first column, 2/3 minus 2/3, 0. And finally, second row times second column gives us 2/3 plus 1/3 is 1. Okay, so it works. It looks like we've done it correctly. That means we could jump right to this step right here. X star is just A inverse times D. So let's see what we get when we multiply A inverse times D. And let me write X star this way. X1 star, X2 star. Because remember, X without a subscript is a vector. Here it's a 2x1 vector. Substitute in A inverse, what we found to be A inverse. Multiply that times the D vector. And the D vector is the vector of right-hand side constant 2, 1. And by doing this multiplication, 2 by 2 times the 2 by 1, we get a 2 by 1. And this 2 by 1 will just be this solution vector. Okay. Multiplying the first row times the first column, we get 2/3 plus 1/3 equals 1. That is our solution value for X1 star. Multiply the second row times this first column, you get 4/3 minus 1/3, 3/3, or 1. So the solution vector is just 1, 1. X1 star is 1, X2 star is 1, and this is the unique solution. Okay. All right. So if I were to give you a problem like this on the exam, I'd expect you to be able to do it this way. Okay. What's the beauty of this approach is this exact same approach works no matter how big the coefficient matrix is. Okay. You just need the coefficient matrix to be square. You need to have as many equations as you have variables for the coefficient matrix to be square. And what else do you need about the coefficient matrix in order to get a solution, in order to get a unique solution? The rows must be linearly dependent. And what's the easy test for that? Determinant. Take the determinant of the coefficient matrix. And as Benjamin, as long as, do you prefer Benjamin or Ben?
I like Ben.
Ben, okay. Ben, as long as the determinant of the coefficient matrix is what? You have a unique solution. That'd be a good test question, wouldn't it? As long as the determinant of the coefficient matrix is not blank 0, then you have a unique solution. Okay. So you run in the definition or the formula for A inverse is this. A inverse is 1 over the determinant of A times the transpose of the cofactor matrix. The only time A inverse won't exist, assuming A is a square matrix, is if the determinant is 0, because you can't divide by 0. For a determinant that's equal to 0, A inverse is undefined, doesn't exist. Okay. But as long as A inverse is not 0, then you know you will have a unique solution. Yes?